It's kind of thank you, Mac. Today is buildings, energy, indoor, that kind of world. So we got a great slate of people to inform us. We got Rahman Azari. I think everyone knows Rahman from Penn State. Michael Waring from Drexel, and then Alexandra. We'll say she's from Berkeley, but she's also from NREL, and she's also from Baltimore. So she covers all the bases. And so I'll hand it over. Just note that in a world full of busy BSEC meeting days, today is like a high point, right? So we've got this now, and then for those of you who are joining at 1 o'clock Eastern time today, we've got a discussion of land surface modeling that I know a bunch of people are going to be interested in. And then at 2 o'clock, we've got the atmospheric dynamics group talking about PBL stuff, right, Darren? Is that the focus today? Maybe Darren's not in a position to talk. Yeah. So planetary boundary layer stuff, right? Yeah. So if you're interested in that stuff and don't know about those meetings and want more BSEC meetings, just put something in the chat. We'll get the links out. And so with that, I'll stop talking and hand it over to Rahman to kick us off.
All right. Thank you very much. And good morning, everyone. Thank you, Ben and Mac, for the opportunity. I'm going to share my screen to get this started. Are you able to see my screen? Very good. Okay. So today I'm going to present some information about carbon emission and, of course, energy use of urban buildings, and provide some information about two projects that we're currently working on. Just to start with some background information, the building industry is a sector with significant impacts on the environment. On one hand, there is this urban population that in the past 120 years have been rising from 13% in 1900 to about the 68%, projected 68% in 2050, and even more in the United States. It is projected that 89% of the population will be living in cities by 2060. So the growth of population in general and the urban population in particular places significant pressure on the construction industry, and we need to address the needs of the growing population. There are all sorts of figures that you could see, some of them here, from 230 billion square meter of new buildings that are needed for in terms of the new building construction by 2060 to 96,000 new homes that must be constructed every day by 2030. So there is a lot of demand that the construction industry is required basically to meet. And then on the other hand, we have all of these environmental impacts of the construction industry and the need to measure and regulate and control all of those impacts. Federal Sustainability Plan that tries to develop some the milestones, if you will, some targets in order to mitigate the emissions of the entire country from 26 to 28% below 2005 levels that must be achieved by 2025 to get to net zero emission status by 2050. And part of that is obviously the responsibility of the construction industry and buildings to meet these goals. We deal with two types of carbon emissions in the building industry. One, we call it operational carbon, and this is the emissions caused because of the energy consumption in buildings. About 2/3 of it is because of the electricity consumption, and about 1/3 is combustion of different fuels that are used for heating, etc. And then the second type of emissions is called embodied carbon, and these are life cycle emissions caused because of the building construction, maintenance, and demolition eventually. So over the entire life cycle of a building, how much carbon emissions is emitted, that we call it embodied carbon excluding the operational carbon. Just to give you an idea of how much these types of carbons are significant, out of 36.8 gigatons of CO2 equivalent that was emitted in 2022 globally, 27% of that is operational carbon of buildings, and 10% is embodied carbon, or all of those emissions because of the manufacturing of several key materials used in construction industry, from concrete, aluminum, glass, brick, and metals in general. So totally, that's almost 37% of the carbon emissions globally that is caused by buildings. And then if we focus only for a few minutes on the operational carbon, as I mentioned, operational carbon is caused by the energy consumption of the buildings. In the US, about every year, almost 98 quadrillion BTU of energy is consumed, primary energy. 39% of that is used in buildings, 21% in residential buildings, and 18% in commercial buildings. And as you could see on these diagrams on the right, huge amount of this energy is consumed for heating of the building, cooling of the building, ventilation, and some of that goes into lighting and plug loads as well. So just by reducing the amount of heating and cooling that we need in buildings, we could potentially reduce significant amount of energy consumption in buildings. So in a conventional building, just let's talk about a typical residential building. The average energy use intensity is a metric that we use to communicate the intensity of the energy use of buildings. That is how much kilobtu of energy we use per square foot of floor area of a building in a year. That is called energy use intensity, or EUI. So the site EUI of a typical residential building is about 53.6 kilobtu per square foot per year. And obviously that is for a conventional building. Obviously the idea is to reduce this site EU of 53.6 to net zero. Net zero energy building is a building that is able to produce as much, almost as much energy as it consumes in a net annual basis. So to achieve that, and obviously from 1975 that we had the first the building energy code by ASHRAE, up to now, there are significant efforts and developments in order to improve the energy efficiency of the buildings. Currently, we are able to design and construct net zero energy buildings. So it's not a research question anymore. It's more of, it's not even a technical question. It's more of convincing people to build more of these buildings and creating a culture around it, creating policies, creating regulations, and making it more economical in order to have more of these buildings. We also, in addition to all of these building codes that are out there that architects and engineers must comply with, we also have this passive house standard. This is a voluntary system that the building owners could decide to follow. And the objective is to design a really low energy and potentially net zero energy building. So based on the type of the building and location of the building and size of the building and the number of occupants, when you decide to build one of these buildings and design one of the buildings, you are provided with certain criteria, certain thresholds with regard to energy consumption and heating and cooling demand of the building that you must not exceed. And there are all sorts of tests and simulations in order to verify the claim that the architect and engineer makes with regard to designing this type of buildings. And the way to do this, passive house standard, usually sits on 5 principles. These type of building have continuous super insulation. They are airtight. They have an optimized solar gain. And in terms of the mechanical system, they use balanced ventilation with heat recovery, and they use renewables as well. So the idea of building a net zero energy building, a net zero operational carbon building, is a possibility currently with current technologies that we have, but we must also challenge ourselves to build buildings that are net zero emission and net zero carbon from a cumulative carbon perspective. So not only operational carbon, but also embodied carbon must be mitigated as well. And embodied carbon is about all of those CO2 emissions that are emitted in the entire life cycle of a building, to extract and manufacture building components, to construct the building, to maintain the building, and eventually demolish the building. Transportation is involved in this process as well, that must be accounted for. And to give you an idea of how much operational carbon exists in building emissions, that is usually 73% of a building's emissions is because of the operational carbon, and 27% is embodied carbon. When we talk about carbon emissions, concrete carbon emissions with regard to embodied carbon emissions, concrete is a major contributor to embodied carbon. 8% of global GHG emissions is because of concrete, and this is a material that we use a lot in buildings, primarily for structural applications. And concrete is, by the way, the second mostly used material in the world after water. And so the construction industry has come up with alternatives, low carbon alternatives for concrete and steel that we use in buildings. Glulam timber and cross-laminated timber are 2 alternatives that we typically use in buildings. And please forgive me if some of this information might sound obvious to you all or some of my colleagues, but I think these are helpful information. And as you could see in these images that I have stolen from internet, you could see that the idea of timber buildings has been applied in high-rise buildings as well. So even high-rise buildings are now using timber, completely timber for the structure, superstructure of the building. So 2 projects that we received funding about a year ago that we're currently working on is the projects that we are trying to deal with both operational and embodied carbon. URBAC and UMOC are twin projects that URBAC has been funded by Penn State Institute of Energy and Environment and Global Building Network, and UMOC has been funded by Penn State Stuckman Center for Design Computation. And both of these projects are collaborative projects. Professor Yulo, one of my collaborators in these projects, are here on the call and is part of the BSEC project. So it's the privilege to be working with these great collaborators on these 2 projects. So URBAC is urban embodied carbon. At the scale of 1 building, we have the methodologies. We know how to measure the embodied carbon of 1 single building. But when it comes to the scale of the urban, it is the methodologies are not fully developed yet. There's a lot of limitations and uncertainties with regard to measuring embodied carbon at the scale of a city like, for example, New York or other cities. So in this project, both of these projects, we are trying to measure the effects of all of these housing scenarios and housing density alternatives on the carbon emissions of urban buildings in the Manhattan, as is the case study for both of these projects. In the second project, UMOC, urban modeling of operational carbon, we are trying to use the data that exists for New York, and other data exists for other cities as well. And we're trying to use data-driven methodologies in order to understand the effect of housing scenarios on carbon emissions. In both of these projects, we're trying to combine bottom-up and top-down approaches in embodied carbon. To assess the embodied carbon of a building, we usually work with the digital model of a building, and then we use life cycle assessment in order to understand the global warming potential of a building, and that would be the embodied carbon. And then the side benefits is that we are able to get data about other environmental impacts and even social costs and health impacts through the life cycle assessment when it applied on a building. From a top-down approach, we're combining material flow analysis and urban metabolism in order to understand the flows of energy and materials at the scale of the city. So that is URBAC. And then for the second project, UMOC, urban modeling of operational carbon, again, we're combining top-down and bottom-up approaches. From bottom-up modeling perspective, we basically need to assess the energy consumption of a neighborhood or a city, in this case, Manhattan. So we're using Rhino plus Grasshopper and UMI. UMI is a plugin to Grasshopper that is used for assessment of energy at neighborhood scales, and the tool developed by MIT. So we're using that to assess the energy consumption of the building or neighborhood, and then use that information to understand what is the operational carbon. And in the top-down approach, we use several databases. One famous database that is available nationally is REX, Residential Energy Consumption Survey. This is valuable data available publicly that we're using. And then we're integrating that with energy benchmarking databases that is available for major cities, including New York, Seattle, and other cities. And we're applying machine learning methodologies in order to understand the interrelations between so many variables that affects the energy consumption and carbon emissions of cities. So that was a quick introduction of what we do, and I would be happy to answer any questions that you might have.
Maybe I'll suggest that we do, a quick question or two, and then do the other talks and see how much time we have remaining, since we have two more. But any quick reflections on what Rahman said? We can also use the chat, of course, for this. All right. Given how much material we have to cover, then thank you so much, Rahman. Let's move on to Michael, and I'm sure that there'll be more discussion of everything you just presented. Really, really useful information.
Hold on, I'll get back. Can everyone see the screen?
Yeah, you're
Yes,
good.
okay, thanks. So just to preface, my computer sometimes lately has frozen up in the middle of Zoom presentation. So if it does that, I have a backup planned with Brian Cummings, who'll show my slides and I'll talk, but hopefully it won't come to that. So just if it does, I'm sorry. So thanks everyone for attending. Michael Waring, I'm a professor and department head of civil architectural and environmental engineering at Drexel. Today, I'm going to talk about our indoor air quality modeling tool, Images, that I've developed in close conjunction with Dr. Brian Cummings, a research scientist at Drexel. So Images, as you can see, stands for Indoor Model of Aerosols, Gases, Emissions, and Surfaces. So why model indoor air quality? Because we have strong indoor sources, and the fact that we spend most of our time indoors, it follows that most of our exposure to pollution occurs in indoor environments as well. Models of indoor environments can range from quite simple to quite complex because of the myriad pollutants and processes that occur indoors. So one of the first major indoor models was published in 1986 by Bill Nazaroff and Glenn Cass, and it considered indoor air from a well-mixed continuous flow perspective. So The simple form of this model shown here applies to either particles or gases, but it does assume inert non-reactive pollutants. So what do we see here? On the left-hand side, we can see we have the concentration accumulation term. On the right-hand side, we have different groupings of terms that show sources or loss combinations. So the first group of sources is from outdoor air being introduced inside due to different airflow types, et cetera. The second main term on the right-hand side accounts for direct indoor emission of pollutants, which can be quite considerable. And then finally, the third term on the right-hand side accounts for all the losses of the pollutants indoors, including flows to outside, filtration and deposition, et cetera. So various new implementations have been added to this simple framework over time. One major implementation was moving from modeling bulk particle mass to modeling instead particle size distributions and dynamics. Particle behavior is most strongly influenced by its size. So this change allowed a detailed understanding of modeling sources and loss processes from a distribution perspective, as well as including things like coagulation indoors. Understanding particle size distributions also allowed us to explore the detailed impacts of filtration, surface deposition, and also to predict lung deposition, because deposition is very size dependent. Another major implementation is the inclusion of chemical reactions into the mass balance. So this is extremely important indoors. Indoors, ozone is a major initiator of indoor chemistry. It can react with unsaturated compounds that are emitted indoors called terpenes or unsaturated alkenes, which are common scenting agents emitted from numerous sources inside, such as air fresheners, cleaning products, among other things. So these ozone terpene reactions, what they do is they initiate a complex chain of reactions producing pollutants such as formaldehyde and other oxidants such as hydroxyl radicals. But extremely importantly, these ozone terpene reactions can also yield high molecular weight, low volatility products that actually partition into the particle phase and produce particle mass in the form of secondary organic aerosol. So one thing, however, missing from these models so far that we tried to do with images was to include a detailed understanding of what the composition of indoor aerosol looks like, so that if we know the composition of indoor aerosol from a broad sense, then we can include various other physicochemical properties, phenomenon, and chemical interactions. And so that's what I'm going to talk about now is our images development. So images, it starts from the recognition that particles are not static entities, right? They exist in a dynamic state whereby dynamic equilibrium is assumed between gas and particle phases in the air environment, okay? So, in fact, the precise definition of an aerosol includes the fact that there's matter in both gas and particle phases, right? So images recognizes that particles are composed of various broad classes of material, both organic and inorganic, and that some of each of the main types of these range from non-volatile materials that always remain inside the particle phase and don't volatilize, all the way to semi-volatile products that can continuously partition back and forth in and out of the particle phase itself and respond to thermodynamic state, okay? So the aerosol composition itself is also not fixed. Images can include alterations by chemical reactions, either in the gas phase of air and also within the bulk particle phase. And then finally, it also recognizes that particle phases can transition itself from a state of being liquid-like to being semi-solid to being a glass solid phase, depending on the thermodynamic state around it. And that this phase state itself directly changes the bulk particle viscosity, which can then either inhibit or facilitate chemistry or inhibit or facilitate thermodynamic partitioning. So why do we do this, right? These implementations and images are relevant because they really correspond to the types of processes that we see going on indoors. So for instance, we have a range of temperature differences that occur due to outdoor weather, outdoor to indoor temperature differences, which affects outdoor to indoor thermodynamic partitioning when particles move inside. We also do many things indoors that emit pollutants such as cooking, which often dominates organic emissions, and cleaning, which emits chemicals that are reactive with ozone and that produce products that change particle composition following gas phase reactions. All right, it's also the thermodynamic nature of images allows us to represent the impact of partitioning of different gases in the air to indoor material surfaces, right? So there's an extremely large surface area to volume ratio indoors, something on the order of 3 per meter. And so what happens is that all the indoor air interacts with those surfaces, and then films develop on those surfaces that can be reservoirs for many harmful or reactive compounds. So what we've really tried to do with images then is to adapt the previous mass balance model that I've shown you to then efficiently capture these thermodynamics I just described in chemistry that affect indoor particle concentrations and thus indoor particle exposures. So what we have now within the model are distinct mass balances for different major classes of the organic and inorganic pollutants, tailored to represent their individual behaviors and interactions. Okay, so I'm going to focus mostly on organic aerosol today. I'm going to demonstrate how images works for modeling organic aerosol indoors. So first, it assumes that organic aerosol follows absorptive partitioning theory. So what that means is that if we have an increase in particle mass indoors, then we can have more partitioning. We have a larger reservoir, and we can have more partitioning of organic material from the gas phase into the particle itself, which will increase particle mass. So more mass, more gas to particle interaction. So, and what that means is, since we're considering this partitioning, what we're really talking about is volatility of the organics in the indoor air, right? And so the volatility of an organic species largely determines its existence in either the gas or particle phase as well. So high volatility stuff will stay in the gas phase, low volatility stuff will form particles. So we represent the amount of organic mass in the air of different volatility using what's called the volatility basis set, or the VBS. Okay, so this is really the heart of the organic model in images. So the VBS, what it does is, instead of just tracking OA as one lumped mass, it breaks it into bins of differing volatility and tracks those bins instead. So the VBS discretizes lumped organic material according to its volatility by what's called the effective saturation concentration. So that's how we organize it. And this is just the concentration above which we start to get condensation out of the gas into the condensed phase. So this is the thermodynamic metric, okay? So on this plot here on the right, we show organics binned by the log of the effective saturation concentration, C star. And then for each of those bins, separated by volatility, the mass concentrations of the organic species in each bin. So note that we don't care explicitly about what the gas is, we just care about its volatility, C star, and its amount. So then with this accounting now indoors, we can now apply a mass balance to each bin. And then since we know the way that volatility changes with temperature, we can also use equations such as the one shown here to account for how volatility changes as temperature changes indoors. And then we can then put all that together with partitioning equations, and OA concentration and attributes emerge. So if we then know, right, what the VBS looks like inside for some organic aerosol, we can just apply these two equations on the right, and we can predict how much of it's in the gas phase and how much of it's in the particle phase, and how that changes with temperature. Okay, so in this example here, about 12 microgram per meter cubed is in the particle phase in green, but about 24 microgram per meter cubed of total organic mass concentration exists inside. Okay, so not only does the VBS represent OA thermodynamics efficiently, as I just showed, but we also have really good data for VBS profiles for a variety of different organic aerosol types that are both emitted indoors and sourced from outdoors. So we can have well-informed models that include OA from a bunch of different types of sources from outdoor air, hydrocarbon-like aerosol, biomass burning aerosol, oxidated aerosol, cooking aerosol, and then we also have VBS profiles, though more limited, for indoor sources. Okay, as well as SOA yielding reactions. So I won't talk about this, but images also not only uses the one-dimensional volatility basis set, but can use the 2D VBS, the two-dimensional volatility basis set, which adds a second dimension to the VBS besides C star of oxygen to carbon ratio in the bins, allowing us to determine more specific compositional aspects, as well as chemical transformations, chemistry in the bulk particle phase, and bulk particle parameters. Okay, so I want to just show like a quick example of why this matters, right, before I go on to the model more specifically. So this is why including thermodynamic partitioning in images allows for better predictions of indoor particle mass. So we mentioned that organic material volatility responds to temperature changes. We're also very aware that temperatures can be either cooler indoors than outdoors in the summer, or they can be hotter indoors than outdoors in the winter. So say, for example, in the summer, we have 5 microgram per meter cubed of organic aerosol moving indoors, right? So we've got 5 micrograms coming in. with the VBS represented below. And just the temperature shift alone from 95 F to 70 degree F for that same VBS, that same organic material, would cause volatility shifts and repartitioning of the OM mass, which results in an increase in organic particle concentrations from, instead of being 5 as it was outside, just by coming inside and being cooler, we get an increase to 6.8 microgram per meter cubed of particle mass due to the lowered volatility. Okay, conversely, in the winter, we see the opposite. If we have that same 5 microgram per meter cubed of organic aerosol moving indoors, then if we get hotter, if we have a temperature change from 25 to 70 degrees F, that actually causes a volatilization of the particles and a decrease in particle concentration mass from 5 to 2.5 microgram per cubic meter. So that's the same reason, but the reverse effect. So I'll note here that, though I'm talking about our model, this is not just theory. We've observed this phenomenon. So at work at Drexel, with, BSEC researcher and my close collaborator, Pete DiCarlo, we've actually measured with aerosol mass spectrometry these temperature-driven increases or decreases in particle mass as outdoor air comes inside. So as expected, we observed that more volatile particle types responded strongly to indoor temperature swings, while low volatility particle types did not. So we've seen, we observed it before we even really made the model to be able to handle these things. Okay, so that's some motivation and some sort of detailed development of images. So here we'll demonstrate the specific processes that are built into this model. So this is what we'll be using to predict indoor concentrations in BSEC. We start with, let me see if you can see, I'm going to try to use my laser pointer. So we start by considering building characteristics such as leakage, ventilation, surfaces, HVAC, filtration, indoor emissions. We have outdoor air concentrations from organic and inorganic sources. We know the outdoor and indoor thermodynamic states, temperature and relative humidity. We can then consider flows related to the HVAC system. We can either look at flows through the envelope itself, natural ventilation or infiltration, or mechanical ventilation with potential exhaust, mixing box, filtration, changes over heating and cooling coil, and then resupply into the zone itself. Images considers pollutants in 3 phases, as I talked about. We have the particulate matter phase, the gas phase, and then the surface film phase. So I spoke of organic aerosol earlier. Organic aerosol can exist in the particle phase, it can partition to the gas phase, or then it can also partition to the surface phase from the gas phase. And the way that we handle all of that interaction is with the volatility basis set, which I showed earlier. It organizes all of our organic material. We also count and compute the amount of organic water, or excuse me, the amount of aerosol water for our indoor concentrations using growth factors. So we can take the relative humidity, the temperature, and compute how much of that water will be in the particle phase, as well as eventually on the surface film. Inorganic species, we account for ammonium nitrate coming in from outdoors and its volatilization as it approaches a warmer indoor environment and loses mass from the particle to the gas phase. And then we also account for inorganic species that are non-volatile, such as ammonium sulfate, minerals, black carbon, etc. We also have a gas phase chemical mechanism that includes oxidation reactions with ozone, hydroxyl radicals, and nitrate radicals. We include inorganic gas behavior, and then these oxidants react with reactive organic gases like terpenes and alkenes and make SOA precursors, which can sorb to the film or add to the VBS in the form of SOA formation. We also include primary emissions and irreversible deposition. Okay, so a couple of quick applications we've done with images lately. So we've developed a 16-city data set that we use a 16-city data set of historical ambient weather and pollution data, where these 16 cities span US climate zones, okay, 16 US climate zones. This allows us to run our model over different thermodynamic outdoor conditions seasonally and monthly, and then facilitate an impact of what those seasonal and regional trends are in the US. All right, and so we've looked at indoor emissions and housing characteristics from the literature that we include statistically. And then so for instance, over the 16 cities, we can determine PM composition indoors for organic aerosol, inorganic aerosol types, as well as water, where the figure on the right shows the median indoor condition for the 16-city data set. And so as you can see, organic aerosol and inorganic aerosol are both higher indoors due to indoor emissions, with cooking particles dominating. So, I talked a lot about temperature. Since images can account for partitioning changes associated with outdoor to indoor temperature differences, we have also modeled over the 16 city data set the expected error that one would get by not considering that repartitioning impact of temperature. So treating particles, in other words, is non-volatile as is typical in exposure work. So we found that the error depended on PM composition outside, as well as indoor-outdoor temperature differences, that the error followed seasonal and regional trends. Okay, and so you can see with this plot on the right, this is a plot of the error on average in each of those 16 cities by month over the year. Okay, and what we see in blue is there's an overprediction of indoor aerosol in winter months in cold climates that ignored the hot indoor environment effect. And there's an underprediction in summer months in hot climates for the reverse reason. Okay. And so to help other researchers extrapolate results such as this and apply them to regular particle models that don't consider thermodynamic impacts, we also developed reduced order regression models to allow a simple error factor to be computed and the concentrations corrected. Okay, just one more thing, two more things. Over that 16 city data set for each month, we also computed the mass of liquid water in the particle phase one would expect indoors, which allows us to make inferences about the phase state of the particle and determine whether equilibrium was actually reached after perturbations indoors. This is little in the weeds. And we've also started to develop model composition of typical surface films and their evolution and residences. Again, getting back at that reservoir on surfaces impact. Okay, one final slide, changing gears from what we'll look at and what images is to what we're going to do for BSEC. We see images being used in two ways. So the first way uses what we call our transient run manager. All right, and so this runs images in its most specific format, right? We can take detailed chemical measurements. We can take detailed indoor airflows at very high temporal resolution. We can take inputs of outdoor pollutant time series and indoor activity schedules or HVAC schedules and put all of this into a transient solver, use the full thermodynamic capability of images, potentially do multi-zone box models, and then we can output dynamic 1-minute resolution outputs, okay? This is what we would use it for. This would allow us to use images to do validation of our model using detailed observations. This would allow us to get insight into hard to measure parameters, as well as look at very specific HVAC control strategies and building operational conditions and how that might influence exposure and indoor pollution. We anticipate running the model like this when the supersite is up and running. And we've worked with Pete DiCarlo a lot, who's sort of leading the supersite impact, where we would take measurements from his group and others and apply the images model and see if the output matches the input. And then also at the other extreme, we run images in what we call our batch run manager. So instead, we now sacrifice high temporal resolution for just being able to run a lot of different model runs, right? So in this case, we often have day averaged inputs. We treat inputs as distributions. We run many scenarios, up to say, 100,000 or 1 million scenarios. We can run Monte Carlo. We have a very efficient way to run these day average values using images. So these take, instead of time series, they take scalar inputs, they run them through a steady state or a time average solver, usually single zone. We'll often do reduced order thermodynamics. We'll turn off some of the high powered features and then produce scalar outputs for all the pollutants. And so the way we see this being used in images, or excuse me, in BSEC, is that we'll be able to run it and get population level exposures. We can explore things like statistical variance and uncertainty across many different buildings and running the model over all sorts of different types of building stock. And this also allows us, as we've done in previous iterations with the model, as I showed earlier, we can get seasonal resolution, neighborhood resolution, all sorts of things like that. Okay. And so, I appreciate everyone's attention. So maybe at the end we can take some questions, but thanks very much. And look forward to working with anyone who's interested in the model. Thanks.
Great. Thanks so much, Michael. And yeah, let's do questions in the chat at the end to make sure that we have time to hear all of Alexandra's presentation. So Alexandra, over.
Sharing.
Yep, there we go. Over to you.
Okay.
Can you hear me?
Yep.
Okay, cool. Okay, hi everyone, I'm Alexandra Grayson. I am working with NREL this summer as a gym fellow and been helping them with prepping for their equity-based building energy simulations in Baltimore. Okay, so just some context about Baltimore and equity in map form. There's a map on the far left with building age by census block group. This like dark spot right here is just all of Hopkins Homewood. So there's no information there, and maybe I could share. I don't know if you all can still see this, but you can see in areas like of interest like Broadway East, really old building age, and then you kind of go over just a little bit, like a block over, and there's a few newer buildings. You can see these differences also here, really new buildings over here, and some super old ones. And yeah, and then I think also like with these maps, you can kind of tell a lot about how Baltimore is slightly segregated based on some of the roadways. You can also see average income, and then one thing that we were hoping to look at are some of these different variables across time in terms of how we pick our areas of interest. Persistent poverty is a data set that the US Census came out with recently, and it's based on the federal poverty level, but we're hoping to maybe put this more in the context of Maryland's state income to pick a few more areas of interest. And I'll get into some of the areas of interest here, and then a bit more about Baltimore environmental and energy equity. So on the right, you can see some of our areas of interest, just some within the BSEC area. And I know like these are some that we're working on with like the indoor outdoor air quality group. And they touch on some other environmental equity challenges in Baltimore outside of building age and then, you know, income and whatnot. So Brooklyn, Curtis Bay, a few environmental hazards. And then looking at the Emerson Village area, some building vintage differences, a lot of new homes being built in like certain census block groups on one side of a road and a few older ones on another side. And then some transportation infrastructure inequities. That's like right before you hit the rest of the city, from the highway to nowhere. And so a bit of what's on the left, the control of domestic rats and mice, just a bit more about Baltimore's environmental justice landscape outside of those hazards and transportation infrastructure inequities. Some of the early 1940s, some environmental justice hazards were possibly exacerbated by researchers from across the country. And so I guess that context, and also looking at the indoor impact of some environmental hazards like domestic rats and mice would be useful and something that we're interested in. Yeah, and so for some of the motivation goals in the workflow, we are aiming to do more equity-based simulation. So first, in terms of defining area, so that's what we've been working on this summer, and then also in terms of building out an XLRM framework that could inform or I guess interrupt also some parts of the URBANOpt modeling workflow. And so, but a lot of the workflow is just like building out like the data. So what's in red is sort of what I've been working on this summer. And I'll spend most of the time talking through the data, I guess. Here's what I've been working on a little bit. And then also working with Tasneem and Elliot on some of these things in yellow and gray. So for the XLRM framework, started with a literature review. For future work, Tasneem and I have been working on a survey and community engagement, XLRM and like informed XLRM for building energy efficiency and other challenges. And so I think we all know what it is now. I think this is context for another presentation. But yeah, some that we're looking at are climate uncertainty, funding uncertainty, and hoping to gain more insight from policymakers and other developers and people involved in the building energy efficiency planning and implementation landscape about adoption rates and in terms of those external factors, and then also in terms of the metrics, hoping to get insight from those interviews as well, but from the literature review finding that these are important metrics in different building energy efficiency scenarios. And so few data sets that people tend to find building energy modeling information from, looked a lot at different government sites, so Maryland property data. They didn't have a lot on houses of worship. So there's a data set from Homeland Infrastructure with all the parcels for houses of worship, and then identifying the vacancies in Baltimore City through the Baltimore City Open Data Hub, but through like in-person surveys found that they were more vacants than even that were indicated on there. So that was interesting. And then from Redfin, looking at HVAC system type, number of bedrooms, and from in-person surveying, HVAC system type from the external building type and number of stories above ground. Yeah, and then a lot of this will be supplemented through res stock where the surveying didn't take place. So here are a few of the systems that I saw on churches, schools, and residences in Baltimore. A lot of these are pretty advanced. There were a few buildings, I didn't put the pictures in here, where there was no AC, or yeah, like really poorly maintained like window ventilation. Yeah, and this isn't a part of what I've been working on, but just for context, a lot of what will be filled in terms of the HVAC system types in Baltimore will be done through Restock. And here are some of the other fields that we could possibly validate in the future. And so for weather data, a bit of what I've been working on is taking those WRF outputs that Elliot made for the group and putting them into TMY3 format, which is usable for URBANOpt, which took forever, but here's a bit more about the importance of the weather file. And for building energy simulations. And we're using the local WRF run just because it's slightly more accurate, and I will be working on some way to show that. Yeah, that's all. Thank you.
Cool. Thanks so much, Alexandra. All right. So we've got a few minutes left. We can take questions for Alexandra or for Michael or for Rahman. Let's open it up. Chat.
Well, so I'll start. So the we have a big focus in BSEC on community input and stakeholders, and what are they concerned about, and it strikes me that there's nothing that people are more concerned about than indoor air quality. And so how has that component of the research been developing? Like, you've got some complex models, and so have you been spending some time talking about what are stakeholder concerns and what's the interaction with the
well, we haven't quite gotten to the community meeting phase yet. What we are, I didn't talk about it today. We talked about it at the all hands meeting. We are trying to develop an outdoor to indoor air quality pilot tool which is able to, it's trying to understand disparities that exist by neighborhood due to housing stock differences and potentially outdoor air differences in indoor exposures to outdoor air pollution. And then the idea would be to be able to model that seasonally, because I think, HVAC changes and window opening behavior changes, and start to understand what these disparities are. And in conjunction with developing that tool, there are people on there, and we're working through this, but we have plans to reach out to the community and try to see if we can learn from them what types of questions they might want us to be able to respond to using the tool, and also eventually to do sort of education in both ways, where we could maybe model impacts of behavior on exposures and identify things that could maybe help people. But also, maybe eventually run different scenarios through the simulation tool where we're able to look at the effects of maybe different incentivization programs around the city to try to help either say weatherize homes or improve HVAC or something like that. So it's like kind of a long-winded answer to say not quite yet, but we are anticipating moving in that direction. And those are the ways we're anticipating moving in that direction from the air quality perspective.
I have many other questions, but I will yield to the other scholars who have politely raised their hands.
Yeah, jump in.
Darren was first. I'll jump in then. So I got a kind of related question. And so Alexandra showed had like 4 neighborhoods that were listed. So I guess I didn't quite understand, well, if they were the 4 focus neighborhoods, but they didn't seem to overlap with the neighborhoods that we're focusing on the start for other activities within BSEC. And so this is a question, why are those neighborhoods being chosen, and should we be concerned about having the other like Broadway East or Old Goucher or those kind of neighborhoods at least be one of those?
Yeah.
So I might have gotten wrong. I guess my first question is, are those 4 neighborhoods the 4 neighborhoods that the group is focusing on at the start?
Mm-hmm. So sorry, the neighborhoods I called Bel Air Edison / Northwood. That's Broadway East. I
think people in Broadway East would disagree. My understanding is that it's close, but the buildings around Bel Air Edison are quite a bit different than they are in Broadway East, Oliver, and places like that.
Mm-hmm.
Anyhow, okay. I guess we should have a concern that when we do get to the community engagement, if most of our community engagement at the start is the Broadway East, Old Goucher kind of community, then this could raise some questions. I'm just raising that as something to think about.
Okay, sure. Thanks.
Yes, all great talks. Thank you for everybody's inputs and questions already. I had 2 sort of thoughts about both Michael and Rahman's, is that Alexandra was able to put in an XLRM framework to sort of identify some of the issues that were relevant. And is there a plan to do that type of analysis also with those models for both of the first 2 talks?
So I'll just jump in real quick. For the pilot project I mentioned, yes, that is what we're modeling it after. And so we are trying to create a tool that we can pull levers and look at metric outcomes, and where exposure is the one we're sort of starting with. The idea would be like, could we then, develop a tool that included a statistical understanding of housing by neighborhood, indoor exposures that occur statistically by neighborhood, and then what levers could we integrate within that tool to see how we could reduce exposures, right? So again, I talked about maybe weatherization or air conditioning upgrades or things like that, even behavioral changes, right? These are the kind of things that we would explore in the XLRM framework to be able to see how the associated metric of exposure and health outcomes was influenced.
Would you be considering Sorry, Rahman, I just a follow up will you be considering the atmospheric conditions on the outside then as well?
So they're like an exogenous variable at this point, right? I mean, they're just really like a pressure on the system. I think if we did want to go broaden the idea of what sort of levers could be pulled, could we reduce emissions outdoors? Could we try to reduce urban heat island effect? These are sort of bigger, harder tackleable things, but they could be looked at as levers from a certain perspective.
With regard to GHG emissions and carbon emissions of urban buildings, so there's this cross-cutting theme of urban GHG emissions that Scott and I are co-leading, and there are many people involved. We collectively created an XLRM framework for urban emissions, and we have identified levers, exogenous factors, relationships, and metrics, and we're trying now to narrow down the scope to create a pilot study for that project, for that theme, basically.
Thank you.
All right, I see we're getting pretty close to the top of the hour here. So if there's no more further burning questions, we can thank our speakers again. This is tremendous amount of information. This has been recorded. It'd also be helpful. I don't know if you guys saw in the chat. I think Ken provided a link to a spot where you can put your slides if you're comfortable with that, so that we can all refer back to them. But yeah, a lot to think about here. And Rahman, great. Thanks to Rahman, just put into the chat so people don't miss it as they log off. A link to the XLRM, which is highly relevant to everything we just talked about today. Great. All right. Thanks again, everybody. Enjoy the rest of the afternoon. Take care.
Thank you very much.
Thanks, everyone.